So the preliminary test is literally what it sounds like. It is preliminary, meaning that what this really does is it weeds out really, really badly divergent series. It simply says, okay, we're going to take the limit as a sub n approaches infinity. So the limit as n approaches infinity of a sub n, and we're going to test that. Now, if this limit equals 0, we got to test further. We got to keep on trying stuff. Now, if it does not, if the limit as n approaches infinity of a sub n equals anything other than 0, that thing is divergent. It's not going to 0, and it's not something we need to test further. We can say for certain it's divergent. So this is the preliminary test. So now, okay, we have something that equals to 0. So how do we do this? Let's take an example. So let's take the series 1/2 minus 4/5 plus 9/10 minus 16 17ths plus 25 26ths plus dot dot dot. Okay, so this we're going to have to figure out what a sub n is. We can say this is n squared over n squared plus 1. And now it's going plus minus plus minus plus minus. That tells us we want to add a -1 to the nth power. Why? Because -1 to the first power, that's -1. -1 to the second power, that's +1. And since in this particular case, we start with a positive where n is going to be 1, we want to say n plus or minus 1. So we'll do n plus 1, and I'll stick these guys in parentheses, even though I'm edging into this guy, but we'll be fine. Okay, so now that we've done that, where a sub n equals this thing, we can ask the question, well, what's it going to do as it approaches infinity? So n squared over n squared plus 1, as we get higher values, n squared and n squared plus 1 are a lot closer to each other. So we could, well, does it approach? So we're going to copy this down here. So the limit as n approaches infinity of this thing is going to approach, we're not even really sure. It doesn't approach anything in particular. Now, why is this? Because every other term is flipped. It's broken. It's weird. It behaves in a strange way. So, but what we can say for certain is it does not equal 0. And this tells us unequivocally that this is divergent. Let's do another example here. So in this example, we're going to use n plus 3 over n squared plus 10n, and that's the series from 1 to infinity. So the sum of n equals 1 to infinity of n plus 3 over n squared plus 10n. We want to figure out if this is convergent or divergent. Now, first off, now the reason I chose this one is because we can use L'Hopital's rule, and I just like going over L'Hopital's rule because it's a very, 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 very useful cheat to make your life easier, especially if you're like me and an incredibly lazy person. So, what is L'Hopital's rule? L'Hopital's rule basically says, well, if you have an f of x over a g of x, and you want to know the limit as x approaches infinity, that's the same thing as the limit as x approaches infinity, or whatever your variable is, your independent variable, of f prime of x over g prime of x. So if you just take the derivative of the numerator and then take the derivative of the denominator and you slap those two back in their respective places, the limit's going to be the same as if it were not differentiated in the first place. Each individual component was not. So let's use that rule with this example. So f of x, or f of n in this case, is n plus 3. F prime of n is 1. G of n is n squared plus 10. 10n. G prime of n squared, we're going to use the power rule. That's 2n because we've subtracted the 1, moved that exponent into the to multiply by the original function, plus 10. It's a constant. N to the 0 is 1. And the original power was 1. Move that to the front using the power rule. We now have our two new functions. So we can now say the limit as n approaches infinity of n plus 3 over n squared plus 10n is the same thing as the limit as n approaches infinity of 1 over 2n plus 10. Now that's a really easy limit. That's a really easy limit. Because this thing over here is going to shoot way up. This thing up here, if we were making a little graph here, is just going to be a constant if it were by itself. Now, what does that mean when we divide this thing right here by this thing down here? What that effectively means is we're going to rapidly approach 0. This whole number is going to get much, much smaller very rapidly. This is 0. Therefore, what we can now say is needs further testing. Boring outcome. But what we've now done is we've made for certain that this thing is not a ridiculously diverging series. We can do a bit more testing on this to verify for certain that this is, in fact, convergent. Integral test. So how do we do the integral test? So the integral test can actually tell us whether or not a series is convergent or divergent. If the integral test is fairly straightforward, if we take some series, and we'll say 1 over n, the integral of 1 over n dn, notice how I didn't put a lower limit, equals natural log of n from to infinity. All we want to know is what this function does, what this function does as it approaches infinity. Well, it's infinite. If the upper bound of the integral of your function, the general form being, and we're going to use red. If we take the upper bound of an integral of some function, series a sub n, dn, if it's equal to some constant, series is convergent. If it is plus or minus infinity, series is divergent. Now that's a really useful test. So let's do some examples. Time to press F12 and duplicate the slides. Example 1. If we take the sum of n equals 1 to infinity of n squared over n cubed plus 1. Now let's do the integral. We want the infinite part of n squared over n cubed plus 1 dn. Now we can use u-substitution, but I'm going to use u-substitution in kind of a specific way that I was taught that I think is kind of cool. Let's take this whole thing and we're going to multiply. Now we want to know what the derivative is of this thing. And we're going to say this dn is, if we say this is apple and this thing is an apple, doesn't matter what the heck it is. If this thing is the derivative of the apple, then you just do ln of the apple. if you've differentiated with respect to Apple. You don't have to just differentiate with respect to X or replace it with U or anything else like that. You can differentiate with respect to War and Peace. It doesn't matter what you differentiate with respect to. You could cheat and replace stuff. So how do we replace stuff? N cubed plus N1 plus 1. This is like G of X of N. G prime of N is 3N squared. It's just N squared. But we can force the thing to do the right thing. What do I mean by that? Well, you can multiply any integral by any number. If I were to stick a 3 in here, that's the worst 3 I've ever seen in my life. We can just move it outside of the integral. So what if we just did this? Let's tack that 3 on there. And what do we want to do to make it the same? We divide by 3. Now, here comes the fun part. That's kind of cheaty. It's u sub, but a little different. Let's rewrite this. Of n cubed plus 1 d n cubed plus 1. What is d n cubed plus 1? It's that thing. This makes the whole thing really simple. It equals ln of n cubed plus 1. You want to make sure you use absolute value symbols there. And remember, it's 1/3 of that. Voila. You could do this with u sub, by the way. You could 100% say let u equals n cubed plus 1 and let du equals 3n squared. But I just kind of like this way of doing it because it really is showing you all in one frame precisely what you're doing. And I think that's brilliant. So now that we've got our function integrated, we're going to evaluate it at infinity. Turns out, in this case, it's infinity. Therefore, series diverges. Now, we could also do that preliminary test that we did earlier, where we can say 2n over 3n squared, the limit of that thing as it approaches infinity. We can then do it again, because you can if you use L'Hopital's rule twice, then you get a constant. So then it is 2 over 6n. It's going to approach 0, right? So that first preliminary test requires that we use another test to verify that it is in fact convergent. So that is a really important use of both of those systems, right? Where we were to say that like the whole thing's limit by itself approaches 0. Okay, well that doesn't give us enough information. Well, we just integrated the thing and now it's going to infinity. Now we know, didn't make the second test, so it in fact is divergent. So really what we're doing is more and more difficult to pass tests until there are tests that are incontrovertible. Like this one, where if it does in fact come out positive, it is in fact convergent.